Well, it's my great pleasure to introduce Araujo to give us the last talk of this conference, and she'll be speaking on foliation with positive tangent sheaf.
Thank you very much. So first of all, I'd like to thank the organizers for all the organization. It's been a great week, so thank you. And also thank you for the invitation. So today I would like to talk about foliations with positive tangent sheaf. So this is a joint work with Stéphane Rouel. And let me just, I'm glad that the notions were reviewed in the first talk this morning. So let me just fix the setup for this talk. So I will actually be working with smooth projective variety. So X is going to be a smooth projective variety. And I'll be always working over the complex numbers. I should say that there has been some recent results generalizing some of the things I'm going to talk about to the singular setting, but I will just speak about the smooth case. And F is going to be a foliation on X. For most of the talk, in order to avoid having to put extra conditions, I will be assuming that this is a proper foliation. So we will not allow the whole tangent sheaf of X, tangent bundle of X. And so this is a foliation. In one statement, I will allow F to be the whole tangent bundle, but then I will make sure that I state this. So let me start by saying what is the general message that I want to convey in this talk. So the general message is the following, that if you have a positivity in F as viewed as a sheaf, this yields algebraicity in the fibers of F, in the leaves of F. So this is indeed vague. So what I want to do in this talk is to first of all introduce some invariants so that we can actually measure positivity and measure algebraicity, and make this vague statement into something something precise and quantitative. So before I do that, let me analyze a very early example. So this phenomenon that positivity implies algebraicity has been observed in many examples in the early theory. So let me look at this case. So for instance, when X is Pn, and let me, just for simplicity, even though I could talk about general rank, let's assume that the rank, that the codimension of the foliation is 1. So in this case, in the case of Pn, we have a global invariant, which is the degree. So the degree of the foliation. So this is defined as, I think Jorge mentioned, that if you take a general line in Pn, this will be in general transverse to the foliation, but at some points of the foliation, you will have tangency, and this degree is exactly measuring the number of tangencies of the foliation to a general line. So this is a non-additive integer. And so this was introduced, I believe, by Juanulu, who also classified the cases of small degree. So for instance, he proved that in the case of degree 0, we have this picture here. So in this case, the foliation F is induced by a projection. So here, this is F is induced by a linear projection from Pn to P1. So this looks like this. So it's a pencil of hyperplanes contained a fixed Pn minus 2. So this is all that you get for degree 0. The case of degree 1 was also classified, and there are two possibilities. So either, again, F is algebraically integrable, and it is induced by, again, a rational map to P1, say defined by the square of a linear form and a quadratic form. So this is a pencil of quadrics containing a double hyperplane. Or there is a second possibility. So here there are two irreducible components in the space of foliations of degree 1. In the other case, you have a linear projection from Pn to P2, linear. And here you get some vector, some foliation, let me call it C, a foliation by curves induced by a general vector, by a vector field. Such that your foliation F is the pullback under this linear projection of this foliation by curves. So these are the two possibilities, and I should say that case you can go on. So the case D equals to 2 has been classified. So this is a classical theorem by Cerveau, Lins Neto. So there are 6 possibilities that have been completely described. But we don't need this I just want to illustrate. So let's look at this. Let's try to look at algebraicity in this case. So in the case of degree 0, notice that F is algebraically integrable. All the leaves are hyperplanes. In this case here, in the case of degree 1, in the first case, again, the foliation is algebraically integrable. The leaves are quadrics. But in the second case, it is not, the leaves are not algebraic. So if you, well, it depends on the vector field, but if you take C to be a general foliation induced by a vector field, these curves in P2 are going to be transcendental. And so when you take the pullback, this foliation here, again, it will not have algebraic leaves. But we see that there are, even though they're not algebraic, they are covered by Pn minus 2, by the fibers of this linear projection. So there are sort of a big algebraic varieties that are contained in the leaves. And then here you could also, again, look at what happens in this case. And again, in each of the 6 irreducible components, you can look at either the leaves are algebraic, or, well, they might not be, but again, they contain many algebraic, high dimension algebraic subvarieties in the leaf through a general point. So this is this is just to illustrate the algebraicity. And so let me define, to make things precise, let me define what we call the algebraic rank. Of a foliation. So here F, X, and F are as before. And the algebraic rank is going to measure so this is going to be the dimension of, so the biggest dimension of an algebraic variety that is tangent to the leaf through a general point. So if you fix a general point, you look at the maximal algebraic subvariety through this point that is tangent to the foliation. So if you do this for a general point, this is going to give you a subfoliation of F. So let me just write this. So we know that there exists a linear, a rational map from X to some subvariety Y, let's say dominant and with connected fibers. And so this is capturing the algebraicity in the leaves, and you have a foliation, and there exists a G, a purely transcendental foliation on Y, such that F is the pullback by this rational map of the foliation G. So by purely transcendental, I mean that if I pick a general point of Y, there is no algebraic subvariety through Y that is tangent to the foliation. So all the algebraicity is encoded in this rational map. what the G, this is for any rank. So this is us in this setup here. For any rank, of course. And of course the relative dimension of this map is a lower bound for the rank. And we say, let me define the algebraic rank of the foliation. So this is defined precisely as the relative dimension of this map phi. So as I said, this is precisely the biggest dimension of an algebraic subvariety of Y that it's tangent to the foliation and passes through a general point.
Is phi uniquely determined? Or?
That's a birationally, yes. Yes. Okay, so in this example, in the example, let me say that. Let me put it as a fact. I mean, this is something that you can definitely observe in the classification of low degree. But it is true that we get a bound for the algebraic rank, which is given by n-1 minus d. So you see, if this is equal to 0, it was algebraically integrable. And in this case here, the worst that could happen is that you have algebraic rank n-2. So this is the algebraic rank. And of course, this has to be less or equal than the rank of f, which in this case is n-1. So this is a general fact. And so see here, this is an instance where we are bounding algebraicity in terms of some global invariant of the foliation. So we want to do it more generally for any algebraic varieties. Of course, the degree, well, this is well defined for Pn and for some, well, we can define it for some special varieties, but in general, we need to look at the better invariants. And what we do in this case, in this example, I remind you that Callum has defined the canonical class of the foliation. And in this example, the canonical class of the foliation, one can check that. So in this example, this is all of d plus 1 minus n. So this is something, this is I think Jorge left it, this is an exercise. And then in this case, we see that this is positive. So we see that the anticanonical is ample if and only if the degree is, so let's see, less than n-1. And whenever the degree is less than n-1, then we see that the algebraic rank is positive. So what we say is that under this condition here, we get that the algebraic rank, at least, well, it may not be algebraic, but the algebraically integrable, but the algebraic rank is positive. So in this case, we have algebraicity. And so this is sort of what we want to generalize, and moreover, and here we can actually even bound this. We can measure this algebraicity. So this is in fact greater or equal than the degree of the anticanonical class, viewed as a divisor in Pn. And so this sort of bound is what we want to generalize to a more general situation. So let me start by defining then what we call a funnel foliation. So a funnel F is a funnel foliation if the anti-canonical class of the foliation is ample. And in this case, we can define the index of the funnel foliation. Let me call it I of F. So this is going to measure how positive is the anti-canonical class. So this is going to be the maximum of the positive integers such that the anti-canonical class is M times some ample divisor A. So this is a way of measuring positivity, at least for a funnel foliation. And now maybe I can state our theorem. So what we prove is that we can bound the algebraic rank using this measure of positivity. So we prove that the algebraic rank of a foliation, of a funnel foliation, so let me put it here. So F funnel foliation. So for a funnel foliation, we can bound the algebraic rank from below by this index. And moreover, we can classify the cases in which this bound is attained. So we prove that if the algebraic rank is precisely equal to the index, then we must have X isomorphic to Pn. And there is a linear projection here. I should get n minus the algebraic rank. And there is a linear. So there is a linear projection and a foliation on this. Let me call this M. And G foliation on PM with zero canonical class, such that F is the linear pullback of G. No, so this has been generalized to the singular case, although this part here. So here, not quite, and in fact, in the singular case, other stuff appears. So this generalized cones appear in here. Okay, so as in particular, yes, sure.
In the definition of algebraic rank, why is the potential 1?
Well, this G maybe, okay, this G could be 0. If it is algebraic integrable, this would be just 0. Yeah, this would be a foliation by points. Okay, so let me see. So what I don't want exactly to give you the proof of this theorem, but I would like to explain 2 of the main ingredients that we use to prove it. So let me introduce these 2 ingredients. So ingredient 1 is what we call the Hardeneration filtration. So this is very classical. So let me just write it in this way for Hardeneration filtration. So let me introduce the setup here. So here we will have, again, here X does not have to be smooth, but for now, let me take a smooth polarized variety. So we are going to fix some ample divisor on X and let E be torsion-free on X. Then we can define the slope with respect to this polarization. The slope of E is just I look at the first Chern class of E. I intersect it with N, so maybe let me call N the dimension. No, sorry. So here I want to say, let me call N the dimension of X. And so the slope is the degree measured with respect with this H divided by the rank. And we say that this sheaf is stable or semi-stable. If for every torsion-free subsheaf of E, the slope of E prime is less or equal than the slope of E. So this is the notion of semi-stable. This is very important, for instance, for the theory of vector bundles. That's a condition that we usually impose in order to get a nice moduli space. And the Hardeneration filtration provides a filtration of F by sort of semi-stable quotient. So let me write this precisely. So maybe I want to write it. Okay, so let me write it in. No, not for any subsheaf. I require this. So usually when you saturate it, the slope is going to increase. And so if it is not saturated, you take its saturation and you require it for the saturation. Okay, so what is the Hardeneration filtration? So there exists, given any E, there is a filtration of E. So we call it, so here we have E naught, which is 0, contained in E1, contained in E2, and so on, up to EK, which is the E, with the property that if you look at the quotients, the quotients are semi-stable. And moreover, the slopes of the quotients are decreasing. So we have that the slope of Q1 is greater than slope of Q2, so on. Okay. And it's not too difficult to see that this will imply that these sheaves here, they will also have decreasing slopes. And so, and for instance, we are going to be applying this, for example, to the case where F is a funnel foliation. And when we apply this to a funnel foliation, well, the fact that it is funnel will force the slope to be positive. And so in this case here, because the slope, so the slope of E is positive, which is going to force the slope, say, of the Q1, the sort of the smallest quotient, well, the biggest slope quotient will be also positive. And in this case, we have this very important theorem. So when we apply this to a foliation, if you apply this to a funnel foliation, so let me state this is a theorem. So I'm taking, So I'm taking, if you take E to be a funnel foliation F, then yes, then if you take, we are going to apply it to the case where we take E to be F. And in this case, so this was a theorem, this was a, okay, this is a, so this first appeared in some version in a work of Piaoka. And then it was later done in more generality, independently by Bost and Bogomolov McQuillan. So they proved the following. So so in this case, so I'm assuming that we are in the case of a funnel foliation. If you take, so let I be any index such that the slope of Qi is positive. So the first one for sure is positive. Maybe the second one, at some point, it may stop being positive. But if you take an index I for which this slope is positive, then, well, the first observation, this is not hard. This comes from properties of slope, that the EI defines a foliation. So you started with a foliation, and then by looking at the Hardeneration Filtration, the first few terms will also be define a foliation. So EI is a foliation. But more, so this is, as I said, is easy. But this the important statement here is not only is a foliation, but it has algebraically it has algebraic leaps. So EI is a foliation with algebraic even more, and rationally connected leaps. I will abbreviate this by RC.
So is the hypothesis that E is a funnel foliation, or?
Well, we need, and the only condition that we need is this one here. Okay. Because yes, so okay, maybe I put it this way. So let's assume that the assumption here is that you have a foliation. So maybe I can write this here. So F foliation with positive slope with respect to this polarization H. In particular, a funnel foliation. So if you take any foliation with a positive slope and you look at the Hardeneration Filtration, you produce subfoliations with algebraic and rationally connected leaves. So this is very useful, and then this has been very much used to study foliation. So as a corollary, we see that any funnel foliation has a subfoliation with algebraic and rationally connected leaves. So any funnel foliation has a subfoliation with algebraic and rationally connected leaves.
But the Hardeneration filtration can be reduced to E and 0, no?
Yes, yes. Oh, wait, no, sorry. So the 0, no 0. You have at least the E1. So you do have something here. It could be all of E, and in this case, E would be algebraic. So, for instance, this I think I erased this, but in the case of the degree 1 case, you are exactly in this situation. The one that you have a pencil of quadrics, the E itself, the foliation itself, would be semi-stable. So the E would be the E1. But in the second case, when you have a linear projection, you actually do extract the linear projection, and this is going to be a piece of the Hardeneration filtration. Okay, so this is one of the ingredients, but exactly as Frank pointed out, it does not give you any control on the rank of this subfoliation. We know that there is something, so this proves at least that the algebraic rank is positive, but this does not tell you what the rank is, and for that we will need a second ingredient. So this is what I want to discuss now. So for instance, if you look at the statement here, we want to bound the rank in terms of the index. And in this case here, we sort of want to say what are precisely the leaves of the algebraic part of the foliation. So for that, so in this case, these are linear spaces. And so the second ingredient that we use is what allows us to sort of identify these fibers. So let me state this ingredient 2. So these are, let me put it in a, let's say it in a, so these are sort of ingredient, like you can call them characterizations of PN. So there are characterizations of PN in terms of positivity that, for instance, we will allow us to say that in this situation here, we get that the algebraic part comes from a linear projection. So let me state some classical characterizations of PN in terms of positivity of the tangent bundle. So let me state this classical theorem of Kobayashi and Yoshai. So they characterize PN as the funnel variety with most positive canonical class. So the statement says the following: so if you have X, a funnel manifold, let's say of dimension n, and index I. So the index of a funnel manifold is defined exactly as we did for foliation. So this is the biggest integer that divides the anticanonical class in the Picard group. So what they proved is that, well, first, the index is bounded by n+1. Moreover, so this bound is achieved for sure for PN, and they prove that it is this is actually a characterization of PN. So this is n+1 if and only if X is isomorphic to PN. And they also classified the next case so they show that it is n precisely when X is isomorphic to a quadric hypersurface. I don't think we are going to need this, but let me just comment that one can go even a bit further. So the next case, the case of index n-1. So these are called Del Peso manifolds, and they were classified by Fujita. And for index n-2, again, they have been classified by Mukai. Sometimes we call them Mukai manifolds. No, here this is in general. No, the Mukai gives a complete classification even in the case of higher Picard rank. There are, I think in the case of Mukai and Fujita, there are a few varieties that appear with higher pK rank, but not many. Most of them I will have pK rank 1. Okay, so let me give you some other further, more recent characterizations of PN. So this one I proved with Stefan and Chandra Kovac, 2008. And actually, for me, this was when I encountered foliations for the first time in my work. So what we proved is the following. So we start again with X, H, polarized, smooth polarized variety. And let's say that let's call the dimension of X n. Then what we prove is the following. So if you have, okay, this is not the most general statement, but this is enough for what we want to do. Let's assume that F is a foliation in here. Here maybe it's going to be important to say that okay, we have a proper foliation of X, such that, so this is a foliation. And let's assume that the anticanonical class of F plus, let's say, a foliation of rank R. So if the anticanonical class of the foliation plus R minus R times H, the polarization, if this is psef, then again here X is Pn and H is O1. So this is so here our original statement was a bit different, but in the case of foliations, this is what it tells us. So if you have a foliation such that the anticanonical class is R times an ample plus pseudo-effective, this can only happen for Pn. And moreover, here in this case, the foliation F would be a degree 0 foliation. And let me state a generalization of this by Horing. So this came a few years later. So here maybe I want, yes, so here I take a polarized variety as before, but here I take a foliation, I allow it to be equal to the whole tangent bundle of X. And what Horing proves is the following. So it's something is slightly, instead of checking that this is pseudo-effective, he just checks that the intersection of this divisor with H to the n-1 is positive. So he proves that if minus Kf minus RH, you intersect it with the H to the n-1. If this is positive, then again, XHF will have to be Pn, hyperplane class, and the foliation must be the whole tangent bundle. So this in a sense, what these results are saying is that if you have a foliation that is very positive, and by very positive here, here I just mean that this is minus R times NAMPO is psef, and here I'm just measuring it with this curve class, then we have to have a PN. And
Also, it's in that psef is then 0.
yes. Okay, maybe I should, let me write it like this. And then here, this, I would say that this, okay, sorry, this is actually. Okay, so these are some of the ingredients. I'm not giving you the proof, but maybe the idea is you take the Hardeneration filtration of your funnel foliation, and then you look at the what we call the maximal destabilizing sheet, the most positive part, and it will be very positive. And we use these types of results to say what this maximal destabilizing sheet, give a bound for this maximal destabilizing sheet. So this is sort of the idea of the proofs. And maybe I want to, okay, so maybe now I want to move on, and I want to show you other ways of measuring positivity. And this, as I presented this is sort of very restricted. We are looking at funnel foliations, but most foliations are not going to be funnel. So now I would like to introduce another technique that has been used to measure positivity in a sort of more in a broader way. So this is to consider movable curve classes. So like again here, so let me fix X as smooth projective variety. Actually, for this here, I don't need X to be smooth. But if not, I would have to impose some restrictions on the singularities. But let's say in this case for a smooth projective variety, then we can define a subcone of the Mori cone. So the cone move X. So this is the closed convex cone generated by classes of moving curves. So this is a closed convex cone. Generated by classes of what we call movable curves. So by a movable curve, I mean a curve on X that can be deformed to cover a dense subset of X. So this cone of moving curves, so this is so let me just remark that this is a theorem by Buxon, Demaille, Pound, and Peternel. They proved that this cone of movable curves is the dual of the cone of pseudo-effective divisors. And so that's why they started to be very much investigated. So the movable curve is in this cone if and only if it has no negative intersection with every effective divisor. And so this okay, so let me see if okay, another theorem. So this is so this was proved by Kreb, Québécois, and Peternel. So basically, what I want to discuss now is our extensions of many of these results in the classical setting to the setting of a movable curve class. So the idea is, I hope it is still there. Yes, my Hardeneration filtration that I put there still holds if I define the slope not in terms of a polarization, but in terms of a movable curve class. So what they prove, so what they show is if you take now H alpha, a movable curve class, then there is Hardeneration filtration for a slope that is defined in terms of this movable curve class. So this is the degree of so this is defined as the degree of the sheaf. And then you instead of intersecting with h to the n minus 1, you intersect it with this curve class divided by the rank. So if you define a slope in this way, you get a Hardeneration filtration for this slope. So let me, I'm glad that that's still in the, it is still here in the Blackboard. So let me just, again here, let me just, again, if you given any torsion-free sheaf E, there is a filtration with, again, here maybe I define the notion of semi-stable in the same way with respect to this new slope. So you get a filtration with semi-stable quotients. Here I'm always measuring now the slope with respect to this movable curve class. And so maybe here I can say that, again, what we want to now do is to apply this to foliations. So in our situation, we are interested in the case, so a special case of interest. Yes?
A little question. Does alpha need to be in the relative interior? Or?
No, any movable curve class. You can define this for any movable curve class.
Wouldn't they then take 0, for instance?
Okay, non-zero. So okay, maybe you want a non-zero. Sorry? Yeah, it's sort of almost, yeah, empty. Yeah. Okay, so the special case, again, that we are interested in is in the case we want to apply this when E is a foliation, F. And we want to apply the foliations for which the slope is positive. So foliations such that, so the anticanonical class of the foliation intersected with this alpha, we want this to be positive. So for instance, it could be that the anticanonical is pseudo-effective. Then it will, let's say non-zero, so it would be positive with respect to some movable curve class. So in this case, again, what we get is that the first quotient, or even the first subsheaf will be, again, it's also going to be positive. And then, of course, then we have the next theorem here. So for the usual, the classical slope, we had this theorem saying that if you look at this, the positive pieces of the Hardeneration filtration, they give you foliation with algebraic and rationally connected leaves. And the beautiful thing is that this theorem still holds if you take the slope with respect to a movable curve class. So this, so maybe I will have to rewrite this, but so this is the theorem, recent theorem of Campana and Pound. So what they prove is that in this situation here, so we start with F foliation F of foliation for which the anticanonical class has a positive slope with respect to a movable curve class. For some alpha movable curve class. And take and let I be such that the mu alpha of Qi is positive. So the first pieces, you look at again at the first pieces of the Hardeneration filtration, then again, the EI is a foliation with algebraic and rationally connected leaves. Same statement holds. So here, the corollary here is that if you have any foliation, say with pseudo-effective anticanonical class, so F has psif and non-zero anticanonical class, then it has a subfoliation with algebraic and rationally connected leaves. And so this, of course, this has lots of consequences for foliations. And so, for instance, okay, so for instance, let me just state maybe a stronger version of the bound for the algebraic rank in terms of another invariant. So let me introduce a new invariant for foliation. So let me define okay, so let me so let me take so let F be a foliation. F a foliation on X, and let's assume, say, that the anticanonical class is say big. Or I can define this for any F. I can define what we call the generalized index of the foliation. So the idea is that now I will be able to measure positivity in a much wider context than that of foliation. So if you give any foliation, I can define this what we call generalized index. So this is going to be the soup of all real numbers, such that the minus kf can be written as a t times an ample divisor plus something pseudo-effective. So here, t is ample divisor, and e is it's a pseudo-effective real divisor. So this is another way of measuring positivity, and this applies in a much wider context. And so what we prove is the following. It's just the same statement as before. The algebraic rank of any foliation F is bounded from below by this generalized index. And the same statement method. So this is the first statement. And moreover, if we have equality, again, this characterizes Pn, and the F comes from a pullback under a linear projection. So in this case, X is isomorphic to Pn, and there exists a linear projection M. This M here is n minus the algebraic rank. And there exists a foliation G on Pm such that the canonical class of G is 0, and F is the linear pullback of G. So this gives, as I said, so now this is a precise and quantitative statement. We bound the algebraic rank of a foliation in terms of a measure of the positivity. And so, see how much time I have. Okay, so let me just, okay, maybe I should, I just want to say what are, again, the ingredients are the same as before. So we have the Hardeneration filtration now for movable curve classes. So this is what we have, and the theorem of Campana and Pau. And again, we need characterizations of Pn in the most positive cases. So let me just observe that Horing's theorem does not hold if we replace. So if we replace in this theorem this ample class here by a movable curve class, then the theorem is false. So this theorem, so Horing's theorem, is false if we replace h to the n minus 1 with a movable curve class. And let me give you a very easy example. So if you take if we take an ample vector bundle on X on any Y, let's say ample vector bundle on any smooth projective variety Y, and then you take, let's say, of rank say R plus 1 at least 2. And if you look at the projectivization of this vector bundle over Y, so if you take your class alpha to be a line on a fiber, so here I take alpha to be a line on a PR, so this is a PR bundle. I take alpha to be the class of a line, then you get that this is going to be, and F, let's see, the relative, the F here is just the relative tangent bundle here. You get that this is positive. So if you do this, you check that minus KF minus R. Here I take the tautological times alpha is positive. And we are not in the case when X is Pn. So basically what we proved, so the ingredient that, well, we have to get this, in any case, we can fix this. So what we proved is that, again, if you have, you start with a polarized variety in a foliation of rank R. And if you take a movable curve class, if you assume that this intersection is positive, so now I'm replacing h to the n minus 1 by alpha, then, well, this is not necessarily Pn, as we have just seen, but we prove that this is basically what happens. So X is a generic PR bundle. And so this is enough for the proof of this theorem here, of this bound on the algebraic rank. So I guess this is all that I wanted to say. Let me just mention so there is a recent preprint by Gilles from a few months ago that, well, so it generalizes these results first to the case of some singular varieties X. And he also uses the Seshadric constants to measure positivity, and he has a theorem like this where he uses the Seshadric constants to measure positivity and use it to bound the index. So I guess I stop here. Thank you very much for your attention.
The generalized index, what can be fractional?
Yes. Yeah, so in the same paper, Liu produced many examples with rational values for this generalizing this. Yeah, basically any rational number. If you give me a rational number, I can construct, if you give me a rational number, yeah, I can construct something with that value for the generalized index.
Is it clear that it's always rational, or could it be irrational?
I don't know. I would guess. Okay, I don't know. I think for rational, yeah, I don't know. Yeah, I don't know. Well, you can turn this. Yeah, so yes.
You'd have just like finitely many rational rates.
Yes, probably. I would say that probably it's okay. Yes, maybe you need to, yeah, here in the smooth case, it's okay, but maybe in general, you need to impose put some restrictions in the general case. But
you need to come up theorem for KF or something? Or
yeah, the sort of the rationality theorem for. Yeah, I would say that whenever you have MMP, this is probably rational.
So the integral foliation, subfoliation that you produce is rationally connected or not?
In general, we do not know, but we have another statement that I did not put it here. So this gives a lower bound for the algebraic rank, and this is the only case when you have equality. But if you know that the algebraic rank is at most this generalized index +1, then the leaves are still rationally connected. But if it increases, then you start losing control. But if it's a little bit bigger, then it's still rationally connected. I am the last speaker. I would like I think we should thank the organizers for this very nice conference. Thank you so much. It's been a really great week.